right, let's get into it. Today, we are hacking the body's own internal messaging service. I mean, think about it. There's a system run by just one molecule that controls your heartbeat, helps form your memories, and moves your muscles. It's pretty incredible. So what we're going to do is explore the powerful drugs that can act like master keys, volume knobs, or even kill switches for this absolutely critical network. Let's dive right in.
So here's our game plan. First up, we'll get to know the master messenger, acetylcholine. Then we're going to see how some drugs can basically impersonate it, while other drugs boost its signal by, get this, disabling the cleanup crew. After that, we'll flip the script and look at the blockers, the drugs that shut the whole system down. And finally, we'll step into the danger zone. What happens when this system goes into total, catastrophic overload, and how a clever two-step rescue can literally save a life.
Okay, so first things first. To really get a handle on the drugs, we have to understand the playground they're all operating in, and that is the cholinergic system. I want to kick things off with a question. You see the heart, the brain, your muscles. What single tiny molecule connects all of them? What has the power to slow your heart right down, fire up your muscles to get you moving, and help you form new memories? I mean, the scope of its influence is it's massive. And the answer is acetylcholine, or ACH for short. This little guy is the star of our show. It's the master neurotransmitter for what we call the rest and digest system. Now, its life is incredibly fast. It gets built, it's released to shoot a message across a synapse, and then boom, it's almost immediately destroyed by an enzyme called acetylcholinesterase. Just think of ACH as the messenger and acetylcholinesterase as the super efficient cleanup crew, making sure the signal doesn't just hang around for too long. Now, for any message to actually be received, it needs a receptor, right? A docking station. Well, acetylcholine has two main families of these, and their differences are absolutely crucial. So take a look at the top row there, the muscarinic receptors. You can think of these as kind of like dimmer switches. Their mechanism is a bit more complex, and their response time is in seconds. Now check out the bottom row, the nicotinic receptors. These are more like simple on-off switches. They're lightning-fast ion channels that respond in milliseconds. Perfect for places where speed is everything, like the connection between a nerve and a muscle. And even within that muscarinic family, there's a ton of variety. The M1 and M3 subtypes, for example, they act like a trigger that turns on the faucets for stuff like saliva and sweat, or they contract the smooth muscles in your gut. But the M2 receptor, which you find in the heart, does the exact opposite. It slows things down. It decreases your heart rate and the force of contraction. It's literally the body's own natural brake pedal. Okay, so we get the system now, but how do we manipulate it? Well, let's start with the most direct approach, drugs that basically pretend to be acetylcholine. These are our direct-acting agonists. They are, for all intents and purposes, master keys that fit right into those receptor locks. And our best example here is a drug called Pilocarpine. If you've ever known anyone with glaucoma, you might have actually heard of this one. It's a classic cholinergic agonist that's been a go-to treatment for decades. So what's really cool here is how we can trace a molecular action all the way to a physical outcome. Pilocarpine directly stimulates the M3 muscarinic receptors in the eye. That stimulation causes a specific muscle, the ciliary muscle, to contract. And that contraction physically pulls open a little drainage system called the trabecular meshwork. So more drainage means less fluid pressure inside the eye. It's a brilliant example of how a drug that mimics ACH in a very specific spot can relieve the dangerous pressure of glaucoma. All right, let's move on to our next class of drugs. This is a really clever approach. Instead of adding more messengers to the system, what if we just stopped the cleanup crew from doing its job? Well, that's exactly what indirect-acting agonists do. They block that acetylcholinesterase enzyme, so the natural ACH your body releases just sticks around longer, making its effect way stronger. Okay, so this slide right here, it highlights a huge principle in pharmacology. A drug's shape, its structure, basically determines where it can go. It's like having a key. On the left, you've got physiostigmine. Its chemical structure is like a master key that lets it slip right through the blood-brain barrier, so it can affect both your brain and the rest of your body. But then, look at neostigmine on the right. Its structure is just different enough that it's like a bulky key that just won't fit the lock to get into the brain. It's totally locked out. So its effects, they're only in the periphery, outside the brain. And that one tiny difference, it completely changes the entire game for what these drugs are used for. And their uses are incredibly diverse. I mean, for the autoimmune disease myasthenia gravis, where muscle receptors get damaged, drugs like neostigmine boost that ACH signal to help patients literally regain strength. For Alzheimer's, where brain ACH levels are running low, drugs that can cross into the brain, like donepezil, help improve cognitive function. And in the operating room, neostigmine is what they use to wake your muscles back up after surgery by kicking anesthetic blockers out of the way. So we've seen how to turn the signal up, right? Now let's look at the complete opposite, turning the signal off. The antagonists, they don't mimic or amplify ACH. No, they just get in the way. They sit in the receptor, but they don't do anything, effectively blocking ACH from ever delivering its message. The classic example here is atropine, which famously comes from the deadly nightshade, or belladonna plant. Its key feature is right there on the screen. It competitively blocks all subtypes of muscarinic receptors, M1, M2, M3, all of them. It doesn't pick and choose. It's a non-selective antagonist, which means it silences those muscarinic signals all throughout your entire body. And because it's non-selective, its effects are just system-wide. By blocking those receptors, it dilates your pupils, dries up your mouth and sweat, slows down your whole digestive system, and, critically, it blocks that M2 brake pedal on the heart. The result? Your heart rate speeds up. You can see how all these effects are the exact opposite of the agonists we just talked about. And that's why it's used before surgery to dry up secretions and to treat a dangerously slow heartbeat. Now, there is another class of antagonists worth a quick mention, the neuromuscular blockers. These drugs, like rocuronium, they have one very specific target, the nicotinic receptors right at the junction between nerves and muscles. Their job is simple but profound, to cause complete muscle relaxation, basically a temporary paralysis, which is absolutely essential for many types of major surgery. They really are the ultimate off switch for our voluntary muscles. So we've seen how to fine-tune the system, right? But what happens when that system is pushed into catastrophic failure? This is where understanding this stuff becomes truly a matter of life and death. And that brings us to organophosphates. These are nasty chemicals found in a lot of pesticides and, tragically, in chemical weapons like sarin gas. Now, unlike the reversible drugs we talked about earlier, organophosphates bind irreversibly to that acetylcholinesterase enzyme. The cleanup crew isn't just knocked out for a bit, it's permanently destroyed. The result is a massive, uncontrolled flood of acetylcholine all throughout the entire body.
These symptoms of this kind of poisoning they're dramatic and they're terrifying. It's the entire cholinergic system turned up to 11. Every single gland that secretes anything goes into overdrive. Sweating, salivating, tears just pouring out. The lungs fill with fluid, the gut churns violently, muscles twitch uncontrollably before just giving up and going into paralysis. And in the brain, it leads to confusion, seizures, and ultimately death from respiratory failure.
So how on earth do you fight this? You fight it with a brilliant two-step rescue. First, you give a massive dose of atropine. The antagonist acts like a shield, blocking those muscarinic receptors to protect the heart and lungs from that ACH flood. But that doesn't fix the real problem. So the crucial second step is this. You give a drug called Pilocarpine. This stuff is an enzyme reactivator. It acts like a chemical crowbar, literally prying the organophosphate poison off the cholinesterase enzyme, letting our cleanup crew finally get back to work. As we start to wrap up, it really all comes back to this one central idea. Pharmacology gives us this amazing set of tools for control. We can precisely mimic the body's own natural signals, we can amplify them, or we can just block them entirely, all in an effort to restore balance or to achieve a very specific goal.
So, to put it simply, the agonists are like turning the lights up brighter. The antagonists are like putting a shade over the lamp to block the light. And the poisons, they jam the light switch permanently in the on position, causing a total system overload.
And that really brings us to our final thought here. We've gone from a single molecular switch all the way to life-saving interventions. So as our ability to design drugs that can target very specific receptor subtypes in very specific organs gets even more refined, what does that mean for the future? What's the next frontier for treating these incredibly complex diseases of the brain, the gut, and the heart, all by hacking this one single fundamental messaging system? Thanks so much for watching.